Okay, good morning, Chan Physics. Just wanted to drop this quick one on electric circuits too, so that we're ready for quizzes this week and tests next week. So, trying to push this through real quick. We want to get that fourth test done before the end of the semester, and so you guys will see that this one should be pretty straightforward. We won't be trying to trick you a lot. So, the first problem asks how many volts would five batteries be together? And if you look at this battery right here, right, we can see that a battery has a plus side and a minus side. And so I think what they were thinking was that we're going to put these five batteries back to back to back. Okay. And if you're thinking about electricity, remember that we always think that the current is going to come through the wire. And when it hits the back of the negative side of the battery, it's dead tired, doesn't want to move, doesn't have any energy, goes through one battery, and gains 1.5 volts of energy. And so you can imagine that when it comes out, it's going to have 1.5 volts of energy. Well, then it's going to go into the second battery. It's going to get another 1.5, and then another 1.5, and another 1.5, another 1.5. So all we need to do is multiply 5 times 1.5 to get 7.5. So by the time that electron gets to the other side, it will have 7.5 volts of energy to do something with it. All right, number two, how does batteries how many batteries would it take to be 97.5? Well, we're just going to take 97.5 divided by 1.5. We need 65 batteries in series like this in a row. All right, 3A is a really trick question because it says what happens to a circuit's current if the resistance increases. And so you really need to make sure that you understand there's two possibilities. If it's a series circuit, all right, like this one down here, well, you can imagine that as that electron goes through the battery, was dead tired right here, gets its 1.5 volts of electricity. Now it has to go through this resistor, then it has to fight its way through this resistor, and then it has to fight its way through this resistor. So all three resistors are stopping or resisting the current from going through. And so when we add another one, we're going to make it harder for that current to get through. So if it is a series circuit, if we add resistance, the current has to go down, right? Because they're fighting through more resistors. But parallel is another story. So like in my class, we talked about, well, when we have something in parallel and this electron goes through the battery, starts here dead tired, gets its 6 volts of energy. Well, now it can go here and it can make a decision. Do I want to go here or do I want to go here? Okay, and so when we start opening up extra paths, it's very similar to the idea of a car going down a highway. So imagine a car going down a highway. There's like 5 cars, they're all in a single lane. And then you get to a spot where we open up into 2 lanes. Well, now one car can go this way, one car can go this way, right? And so now it's a lot easier for those cars to get through the highway. And if we go into another section where that road splits into another 2 lanes, well, now we've got even more lanes. And so now all of a sudden traffic gets to open up. It's easier for those electrons. And so the same idea here. If we add another resistor right here, so if we have these two and we add another pathway, well, now it's easier for these electrons, this current to get through. And so even though we're adding a resistor here, we're actually, the total resistance of the circuit is going to go down because now there's more paths for that current to take. And so the answer for number 3A is in a parallel circuit, if we add resistors, the circuit increases because there's more pathways to go. Okay? All right, what happens to the circuit, the current, if the voltage increases? Well, that's just, we've got more power. And the more that battery is allowed to get bigger, right, the more it can push that current through. And so if the battery's voltage increases, the current is going to go up. All right, we'll show that to you in equation form in a couple months, I think. But right now, we just want you to understand the concepts. And so we're just kind of like pushing through the idea that you should get a good feeling about what electricity looks like. All right, so the question 4 is, what's the difference between conductors and insulators in terms of current? Well, conductors allow for high current, right? So if they're conducting electricity, they're allowing for high current. An insulator is going to have low current, okay, or no current. Amount of resistance. So if the conductor is allowing electricity to go through it, you must have a low resistance, because remember, low resistance is like I'm squeezing the pipe, right? And so I'm making it hard for that current to go through. And so a conductor allows for that electricity to go through. So it's going to have a very low resistance, while an insulator is going to have a very high resistance. And the last thing, what types of materials? Conductors are usually made out of metals. Sometimes they have semiconductors made out of silicon, but we wouldn't talk about that too much. Insulators, rubber, plastic, or wood. Okay, so now when we do the circuit diagrams, you just need to know the symbols for the quizzes. It's like the easiest points in the whole physics semester, right? Just to draw a circuit diagram. And so if you don't know how to do a circuit diagram, or you're losing points on these, it just means that you just didn't want to do it. You just didn't want to check out, right? So a circuit consists of a battery, a switch, a resistor, and a light bulb, in that order. So remember that a battery is one long line and one short line with two wires coming out of it. And most of the time people just put the plus on the long line and don't bother with the minus on the bottom line. Okay, so that's my battery. And then it wants a switch. So we're going to turn the corner in this, and we'll open up the switch like that so that we can see that switch. We'll turn this corner again, and we'll draw a resistor. It's just a squiggly line. Right? And the last thing is this bulb. And so a bulb, you just go up, make one or two squigglies, go down, finish off our circuit, and then make a little circle over that. So that is this circuit diagram. Now I didn't do these in advance because I wanted to show you as we were doing this the mistake that a lot of people make on 8. It says a circuit diagram for a circuit that contains a battery, a light bulb, a second battery, and a switch. So I'm going to start out the same. I'm going to draw up my my battery, and then they ask for a light bulb. So I'm going to put my light bulb right here, go up, do two squigglies, and then come down, and then put a circle over it. That's our light bulb. Now they ask for a second battery, and the question you guys have to ask yourselves is, how are you going to draw that? Are you going to draw it like this one, so with a long line here and a short line there, or you're going to flip it? And that all goes back to this idea that you need to be constantly thinking about electricity as electrons moving around, or current moving around this circle. And so when they get to this back of the battery right here, dead tired, they go through the battery, they gain whatever voltage this battery is, right? And then they're going to lose it here in the bulb. And now they're going to go through another battery. And so if I was to make this battery where the long line was here and the short line was here, well, now this current that's going through here will have to fight its way oppositely through the battery, right? It's not going to be able to use that battery to gain more voltage. It's actually going to fight it. So we need to put the short line here and the long line here and the plus side here, okay? Because that gives us the ability to say, okay, now the current's going to gain voltage. It will lose voltage here in the bulb, but then it will gain more voltage here. And then they ask for a switch here at the end. And so we'll just draw a switch, okay? So remember, I always said in my class, it's like your grandmother putting batteries in the wrong way. When the batteries don't go in the right way, they fight each other. And so if we were to do this the other way, where I had the bulb here and I had the battery here, right, we can see that if we try to draw the current coming through this, it would go up here, but this battery will try to draw the current that way, right? And then those two things are going to fight, and we're not going to be able to make it. And so that is, this is the incorrect one, and that's the correct one. Okay, so current always goes from the positive side to the negative side. That's what we talked about. And then series resistance, real simple, right? The idea is that once we recognize that this is a series circuit, then we know that the equation that we're going to use is RS, or RT, is equal to whatever number of resistors added up. So 5 plus 15 plus 10, 30. This one right here, 18. Okay, so the series circuits are the ones like you should be able to get these like for free, right? These are like free points. The only mistake I've seen is some people adding the voltage of the battery, 1 plus 2 plus 6. voltage is completely different than resistance. We're trying to get the total resistance, or the resistance in series that the battery sees. And so we're just going to add the resistors. We're not going to add the battery. So 3 ohms on this side and 30 ohms here. All right. A lot of you are looking for shortcuts. Always in physics. Stop looking for shortcuts. Your teachers have been learning this for 30 years or more. As I tell my students, I went to the University of Illinois. It was number 2 in electrical engineering at the time. We always just did it the way our teachers taught us. Shortcuts get you some quick points every now and then, but then when you're sitting in the test, all of a sudden there's a mistake or there's something that goes wrong and you regret it. So when we add resistance in parallel, what we need to do is remember the right equation. So 1 over Rp equals 1 over R1 plus 1 over R2. Okay? And remember, when we do this, we work down. We don't work across, we work down, so that we remember that we're finding 1 over Rp when we do 1 over 3 plus 1 over 6. Okay? We're going to find the common denominator, which is, in this instance, 6. How do I go from 1/3 to 6? Well, I must have to multiply this by 2 over 2. So 1 times 2 is 2. 3 times 2 is 6, right? So that becomes 1/3 becomes 2 6. 1 6 becomes 1 6 again. And so 1 over Rp is equal to 3 6. Okay? But as my professors at Illinois used to say, I didn't ask you to find 1 over Rp. I asked you to find the total resistance, or the resistance in parallel. So these numbers need to be flipped. If we flip this, we get Rp over 1 is equal to 6 over 3, or 2. So the answer is 2. Now, remember, what we said was, let's say we have this circuit. It's got a 3 ohm resistor, but we add a 6 ohm resistor in parallel. According to question 2, right, if we add resistance in parallels, the resistance should go down. And so we had 3, we added this one, now it's 2. So we see that the total resistance of this circuit goes down. Okay? All right, the last ones I've got written out there for you already. So here's the second one right over here with a 2 and a 3. So 1/2 plus 1/3 becomes 3 6 plus 2 6. Okay, or 1 over Rp is 5 6. We flip them and we get 6 fifths. Okay, and the last one over here, 1/2 plus 1/3 plus 1/2, we get 1 over Rp equals 8 6. So Rp over 1 becomes 6/8, or 3/4, or 0.75. All right, hope that helps you guys. And always remember, you can always come in and ask for help.